Welcome back, everyone. In the last video, I promised you that I would post a video showing the solution for examples 3 and 5 on this note sheet. So that's what we're going to do today. In example 3, we're going to prove the angle bisector theorem. Now, I'm going to show you this in a minute, but you're going to realize as I'm going through that it's going to sound very familiar to example 1, where we were proving the midpoint theorem, which I guess kind of makes sense because if you think about it, an angle bisector is kind of like the angle equivalent of a midpoint on a segment, right? It takes an angle and it divides it into two smaller, equally sized angles, like how a midpoint divides a segment into two smaller, equally sized segments. So the angle bisector theorem, what it says is that if ray BX is the bisector of angle ABC, then the measure of angle ABX has to be half of the measure of angle ABC, and that the measure of angle XBC has to be half of the measure of angle ABC as well. So we're going to prove that has to be true. So we're going to start with the given information that I have a diagram with angle ABC and ray BX is bisecting that angle, right? Now we know, just to mark on this diagram, we know that if ray BX is bisecting angle ABC, we know that it's creating two congruent angles out of angle ABC. So I went ahead and marked that on there just to remind myself that those are congruent because this ray has bisected angle ABC. So statement 1 is, like it usually is, it's the given information. So that reason's pretty easy. It's the given. Statement 2, now I left a couple blanks here for you in statement 2. It's saying that angle ABX is congruent to what? What angle is angle ABX congruent to? Well, you can see we've already marked it congruent to angle XBC, which is to say that the measure of angle ABX equals the measure of angle XBC. Now, how do we know that that's true? How was I able to mark that those angles were congruent when I was putting those marks on there? How did I know to do that? Well, it's because I knew what it meant for something to be the bisector of an angle, right? And so if I knew that it was true because of this word right here, that means that my reason would be the definition of angle bisector. I knew that this had to be true because I knew what an angle bisector did. So that means I was using the definition of what an angle bisector is. Now in statement number 3, I have that angle ABX, its measure plus the measure of angle XBC, equals the measure of angle ABC. Well, how do I know that that's true? Well, anytime I'm adding two angles together and it equals one bigger angle, that's usually a big key that I'm using the angle addition postulate, which says that, again, if I add two adjacent angles together, I would get the measure of the larger angle that their non-shared sides form. So that is the angle addition postulate. That's what tells me that statement number 3 must be true. Now in statement number 4, I got to compare it to statement number 3 and notice what has changed. What's changed is, well, nothing right here, right? The measure of angle ABX comes first, just like it did in statement 3. But then next, in statement 4, it says the measure of angle ABX again. But in statement 3, it's had the measure of angle XBC. So what has happened here? Well, in statement 2, I said the measure of angle ABX was congruent to the measure of angle, or was equal to, I should say, the measure of angle XBC. So you can see what I've done is I've taken this measure of angle XBC and I've turned it into the measure of angle ABX. So I took one thing and turned it into something else because those two things were equal to each other, and that is known as the substitution property. Substitution property. Now the second part of statement 4 is just some combining like terms. Instead of saying measure of angle ABX plus measure of angle ABX, we write it as 2 times the measure of angle ABX equals the measure of angle ABC. So now how has that changed when I get to statement number 5? Well, you can see that instead of 2 of the measure of angle ABX, I just have 1. And instead of the measure of angle ABC, I have half the measure of angle ABC. So what's happened here is I took this entire equation, multiplied both sides by 1/2. So if I'm multiplying both sides of an equation by a number, that is the multiplication property. The multiplication property. Lastly, so that's half of what we were supposed to prove, that the measure of angle ABX is half of the measure of angle ABC. The other thing I was supposed to prove was that the measure of angle XBC is also half the measure of angle ABC. And so that's the statement that I have in number 6. How did I get from 5 to 6? I just put the XBC back in the place of ABX, right? I substituted XBC back in for ABX. So that is, again, the substitution property. So like I said, this should look very familiar. It should look pretty much the same as the proof of the midpoint theorem, where we start with the given, then we use the definition of, in this case, in example 3's case, we use the definition of bisector. Here it was definition of midpoint. In example 3, we used angle addition postulate. Here in example 1, I used segment addition. Then some substitution and multiplication and substitution again. You can see it's a lot of the same type of reasons. So this is very similar to proving the midpoint theorem. Now the last example I told you I was going to do for you was example 5. So let's take a quick look at that. Let's see what's going on here in example 5. The given information is that Wx is equal to YZ, and that Y is the midpoint of segment XZ. Well, that would indicate that YZ and YX are the same. So we have to prove that the distance from W to X is the same as the distance from X to Y. Well, you can see I've already got it all marked congruent, so I've kind of already figured out that this does have to be true, but let's prove why. Let's explain why this has to be true in a proof. So we're going to start with the statement that Wx is equal to YZ, and that Y is the midpoint of segment XZ. And of course, that is the given information. Next, we have that the length from X to Y is the same as the length from Y to Z. Now, I marked that on here, but do you remember why? Why was it that I marked this and this congruent? It had to do with the fact that this statement said that Y is the midpoint of segment XZ. And so I said, aha, I know what midpoint is. I know that a midpoint makes two smaller congruent segments. So the fact that I was able to put that marking on there and say that this was true was because I knew the definition of a midpoint. I know that the midpoint takes a segment and makes two smaller congruent segments out of it. Now lastly, we have a statement that says Wx equals xy. Well, where have we seen Wx before? We've seen it right up here when it was stated that it was the same as yz. Where have we seen yz before? Right here when it said that yz was the same as xy. So what we did was we took this yz right here and I turned it into this wx because yz and wx were said to be equal. So I took this wx, and I put it where this yz was to make this statement, Wx equals xy, so I used the substitution property. I took one thing that was said to be equal to another and flip-flopped them in an equation. I have a pretty short, quick proof for example 5. All right, that does it for this video, so we will see you next time.